Welcome to Deep Learning Theory Seminar. First, I will read some notice and then introduce today's speaker. So here are some important notice about this seminar. First, reproduction is prohibited. And second, reproducing all or any part of the contents is prohibited without the author's permission. This seminar will be recorded and the video will be available on the Recon AIP website later. And fourth, if you have any questions or comments, please scroll to the bottom of the page and click the chat. And finally, this seminar will be given in English. So today's talk is given by Takuo Matsubara. He's a PhD student from Newcastle University and Alan Turing Institute, and his supervisor is Chris Oates. And today's title is Robust Generalized Bayesian Inference for Intractable Likelihood.
Okay, so yeah, many thanks again, Shao, for inviting me to this series. I'm Takuo Matsubara, third year PhD in Newcastle University and the Alan Turing Institute. Today, I'm going to talk about robust generalized Bayesian inference for intractable likelihood. So as this title suggests, we consider Bayesian inference for a particular class of probability models called intractable models. So this is joint work with Jammers and FX, who are both at UCL now, and my supervisor, Chris, from Newcastle University. Okay, so first of all, any probability model, P theta, can be separated into two parts. The first part is unnormalized density, Q theta, and the second part is normalizing constant, Z theta. Please note that this normalizing constant, Z theta, is the function of parameter theta, because this is nothing about integral of the non-normalized density, Q theta. And intractable models is a models whose non-normalized density is easy to evaluate, but whose normalizing constant is really hard to compute. And such situations occurs so often. For example, exponential family is a typical example of intractable models. So exponential family models is defined as exponential of linear combination of the data summary statistics T of your data X and some additive function B. And this, how you combine this summary statistics is your parameter theta here. And this exponential family model is used for example, image annotations or statistical physics or some biostatistics field. Okay. And the second example is more machine learning type example, something called energy-based model. So in this case, you model your probability by exponential of minus some black box energy function, which is often parameterized by neural network or some black box model. As you can see, if this energy function is complex, this probability model P theta can be easily hard to be normalized. Okay. And in this research, we want to consider the Bayesian inference for intractable models. The Bayesian posterior is defined as follows. So here, pi is our prior, and this term in the blanket is our likelihood. And as you can see here, we now assume that our model is intractable model, which means the normalizing constant of our model is very hard to compute. So in this case, I have to explain this. Zx is the normalizing constant of posterior itself. And that this Z theta is a normalizing constant of model. And in such case, the Bayesian inference for intractable models, the standard MCE no longer works because the evaluation of that posterior explicitly requires computing this the normalizing constant of your model. the MSMC method algorithms usually doesn't need this the normalizing constant of the posterior. But as you can see, the model normalizing constant z theta is incorporated inside the posteriors. So at every theta, you have to compute this normalizing constant z theta. And this makes the Bayesian inference for intractable models really, really hard. So the few solutions have been proposed so far to this for this problem. For example, auxiliary variable MSMC or approximate likelihood. Yeah. And but however, some sort of the robustness of this method have rarely considered in this particular context. Okay, so what we want to achieve is to establish some computable and robust Bayesian inference methodologies for these intractable models. Okay, and our approach in this work is a combination of something called generalized Bayesian inference and Stein discrepancy. So at the end, we propose some pseudo posterior in this form. So this pseudo posterior is defined by a product of flyer pi and exponential of Stein discrepancy between our model and the data. Okay, and in this work, we showed that this pseudo posterior have many nice properties. For example, some conjugation, some conjugate. They enable some conjugate inference for some particular probability models, and also they satisfy some consistency, asymptotic normality, and some robustness. Okay, so in this talk, I'm gonna explain this property which this pseudo posterior satisfies. Okay, so the first section of this talk is to recap the background of this research. And in particular, I want to recap this generalized Bayesian inference. I want to recap what generalized Bayesian inference is and what Stein discrepancy is. Okay, so let's go to the background section. The first one is the generalized Bayesian inference. So let's say we have some probability model P theta, and the standard Bayesian posterior is defined as follows. So this is a product of prior pi and your likelihood given some data xi. And if you apply some exponential and log decomposition, this can be also written as the product of prior pi and exponential of log likelihood. And what generalized Bayesian inference do is to replace this log likelihood term with something else. Okay, so this generalized Bayesian inference replaces this log likelihood term with any other arbitrary data-dependent loss. Okay, so in short, this is the generalized Bayesian inference. Okay, for example, if you choose negative log likelihood as this data-dependent loss function, you can recover the standard Bayesian posterior. Okay, so in other case, you can also pick, for example, alpha divergence for this data-dependent loss, or some score matching type divergence. So the point is you can plug in any loss function into this D here. Okay. So this is generalized Bayesian posterior or generalized Bayesian inference. And the motivation why we want to use generalized Bayesian inference is model misspecification. I'm going to explain this about this in this following video. So let's say this circle indicates our parametric family, our parametric model family, and this P indicates the true data generating distribution. So when we say our model is well specified, if this true data generating distribution is included inside your model family. On the other hand, we say our model is misspecified if this true data generating distribution is outside your model family. Okay, and from some information theoretic perspective, we already know the standard Bayesian posterior is optimal when your model is well specified. Okay, but on the other hand, if your model is misspecified, there is no optimality guarantee for any type of posteriors. So if you change the sort of the criteria to measure the accuracy of your model to the data generating distribution, then this might improve your estimation result at the end. So this is the first motivation why we want to use the generalized Bayesian posterior. Okay. Yeah. Okay. I think I can omit this second part. But this generalized Bayesian posteriors also have other justification based on some optimization centric perspective. So recent findings reveals that the Bayesian posteriors can be obtained from some optimization problem. So this generalized Bayesian posterior also follows the same optimization procedures. Okay, so this was the very quick recap of the generalized Bayesian inference, and the second recap is about Stein discrepancy. Okay, so the Stein discrepancy is a divergence between two probability measures. And in order to define Stein discrepancy, we have to define something called the Stein operator first. Okay, so let's say we have some operator SQ from some function set H to other function space L1. I just denoted this as L1 here for simplicity. Okay, and we call this operator SQ Stein operator if this operator SQ satisfies the following zero identity. Okay, so first we take some function H and then apply this operator SQ. And then we take expectation of this value with respect to distribution Q. And if this expectation is 0 for any function H, then we call this operator SQ Stein operator. Okay, so I think this is a little bit confusing. So I want to take some specific example of Stein operator. That is the Langevin Stein operator in the second line. Okay, so this Langevin Stein operator is defined as the product of the log derivative of some distribution Q and the input function H, and plus the divergence of the input function H. Okay. And we can actually show that this operator satisfies this zero identity for any input function H. Okay, so in my talk, actually I actually use this Langevin Stein operator throughout my talk. Okay, then we are ready to define Stein discrepancy. So the Stein discrepancy is then defined as the maximum deviation from the zero identity. Okay, so this is how we define Stein discrepancy. So we take some input function H first, then apply our Stein operator SQ for this input function H. Then we take expectation with respect to P. So I'd like to remind you that in the first equation, we take expectation with respect to Q. But in this definition, we take expectation with respect to P. So, and then finally, we take supremum over all possible function H. And then here's what's going to happen. So if this distribution P get closer to Q, this quantity inside a supremum also get closer to the zero identity here. And because of the property of this Stein operator, if this P get closer to Q, this expectation must get closer to 0 because of this zero identity. So in this sense, this Stein discrepancy defines some sort of notion of closeness between two probability distribution P and Q. So this is the basic definition of Stein discrepancy. Yeah, and we have a few of remaining questions about this Stein discrepancy. The first question is how to compute this primum in practice. Of course, in theory, this primum might not be so problem, but in practice or in computation, we actually have to compute this primum. So the first question is how to compute this primum. And the second question is, okay, so the second question is how reasonable this Stein discrepancy is. Maybe some of you might understand that this Stein discrepancy introduce some sort of closeness between two distributions. But one may wonder how reasonable this criteria is. And the last question is one of the most important part. What is the computational advantage of this Stein discrepancy? So let me go for the first one. So yeah, the one of the most common choice to compute this primum is to take something called reproducing kernel Hilbert space as a function set, capital H here. So in interest of time, I think I have to omit the detailed explanation about what a reproducing kernel Hilbert space is. But in very short, the reproducing kernel Hilbert space is some special Hilbert space, which can be uniquely associated with one kernel function K. So this is the something called the reproducing kernel Hilbert space. And because of this one-to-one correspondence, we can analyze the property of this reproducing kernel Hilbert space through this kernel function K. Okay, and using this reproducing kernel Hilbert space, something very beneficial happens. So if we choose this space of input function H as this arcade H is here, we can have the closed form solution of this primum term here, like this. Okay, so as you can see, okay, so we apply this Stein operator for both argument of the kernel. The first Stein operator is applied for the first argument of kernel, and the second Stein operator is applied for the second argument of kernel. And then we take the expectation with respect to Q for both argument of kernel. Okay, so this is actually the closed form solution of this primum term here. Okay, and this is very advantageous in practice because we can just compute this divergence using the Monte Carlo integration in practice. Okay, so the second question was how reasonable the Stein discrepancy is. And so again, in interest of time, I have to omit the detailed explanations. But in short, under some nice regularity, this KSD implies weak convergence of the probability measures. Okay. So we can say, this Stein discrepancy is, at least some nice measurement criteria to measure the closeness between two probability distributions. The last question was, what is the computational advantage of this Stein discrepancy? Okay, so this is the most important part for my research. So if you take if you take this kernel Stein discrepancy for your model and data, you will find this kernel Stein discrepancy doesn't depend on the normalizing constant of your model. And here's the reason why. So this kernel Stein discrepancy depends on your model through this Stein operator here. Okay, and this Stein operator use the log derivative of your model. And by simple calculations, it turns out that this log derivative doesn't depend on normalizing constant of your model, because the log derivative can be transformed into the derivative of your model over your model itself. So because of these fractions, your normalizing constant is just canceled out. Okay, so this is a wonderful thing. This Stein discrepancy, doesn't depend on the normalizing constant of your model. Okay, so this is a very super quick recap of Stein discrepancy. And now we are ready to define Stein, our pseudo posterior, which we call Stein discrepancy base. So the definition is really simple. We use the framework of generalized Bayesian inference, and we choose the loss function as the Stein discrepancy. So at the end, our pseudo posterior have the form, the product of prior pi times exponential of Stein discrepancy between our model and the data. Okay, and we often use the kernel Stein discrepancy. So in that case, the form of a pseudo posterior is written as follows. Yes. And as you can see that this pseudo posterior can be computed using our data and without the normalizing constant of the model. So by using these pseudo posteriors, we sort of succeeded to eliminate the normalizing constant of the model from the definition of the posterior. And because of this, any standard MSMC algorithm are applicable to sample from this pseudo posterior, even if your model is intractable. Yes. And if we choose the kernel, very carefully, it also gives you some robustness, which we discuss later. And the additional bonus of this posterior is conjugate form for exponential family. Okay, so let me summarize this, right? If we use exponential family for some application, and if your prior is Gaussian, then our pseudo posterior also becomes Gaussian. So this is quite a nice bonus. Because in this case, we don't have to apply any MSMC or other bidirectional inference or something. We can just sample from our posterior analytically, so which is amazing. Okay. So this was the basic recap of our methodologies and definition. And now I'd like to move on to the theoretical properties of these posteriors. Okay, so this posterior satisfies these properties: posterior consistency, asymptotic normality, and the bias robustness. So I'd like to begin with this posterior consistency. Okay, so let me explain about posterior consistency using the figures in the middle of this slide. So let's think this yellow line is a loss function of the generalized Bayesian posterior, or in other words, that this is the criteria to measure the accuracy of our model. And this blue line, let's say this blue line is the posterior distribution. So what posterior consistency says is, if you observe infinitely many data, your posterior, this blue line, get closer and closer to the global minimizer of your loss function. Okay, so intuitively saying, this is what posterior consistency says here. And this property can be shown with a quite mild assumption called prior mass condition. So what prior mass condition says is your choice of prior have to have certain amount of probability mass in the neighbor or over the neighbor of the global minimizer theta asterisk. Although this condition is quite difficult to verify in practice, but as you can see, this is not extreme condition. This is not so much strong conditions. And under these conditions, we can prove this posterior consistency with some non-asymptotic rate. And one thing I'd like to emphasize is that now the situation we are considering in this case is, okay, so in this case, model doesn't have to be well specified. So this result covers the case of model specification as well. So this theorem holds even if the true data generating distribution is lies outside of your probability model. Okay, so yeah, so our pseudo posterior satisfies this posterior consistency. And the second result is about asymptotic normality. Okay, again, I'd like to explain about this using the figure in the middle of this slide. So if we observe infinitely many data, our pseudo posterior looks like Gaussian in the neighbor of the global minimizer. So in the previous result, we saw that our posterior concentrate around the global minimizer theta asterisk of our loss d. And if we zoom in to the neighbor around this global minimizer theta asterisk, the shape of our pseudo posterior looks like Gaussian. So this is basically what this result says. Okay, so and this is assumptions for this asymptotic normality result. And this assumption basically says our loss function have to be 3 times continuously differentiable. Okay, so yeah, roughly speaking, if our loss is 3 times continuously differentiable, then we have this asymptotic normality result, which is often referred as to Bernstein formation theorem. Yes, so if we observe infinitely many data around the neighbor of the global minimizer, our pseudo posterior behave like Gaussian. Okay, and last theoretical property is bias robustness. And the bias robustness is one criteria to formulate certain robustness. Okay, so to formulate this concept of bias robustness, I'd like to consider something called epsilon contamination model. So let's say this gray histogram is our data, and let's think some situation where we add some outliers to our data set, which is denoted by Y here. So this is equivalent with thinking about the mixture of 2 distribution, our data distribution, and some Dirac mass at this outlier point Y. Okay, so this is the basic situation we want to think here. Okay, so And this biased robustness is originally developed in the frequentist context. So again, let me explain about this concept in using the figure. So that let's say we want to construct some estimator of a mean of our data set. So this blue line is the mean estimator. And in the top figure, there is no outliers. And in the second figure, we have outliers here. And if we apply the same mean estimator, we would expect this estimator would be shifted towards the outlier. Yes. And if you add infinitely large outlier to your dataset, and if this shift denoted by delta here is bounded somehow, then we call this estimator is bias robust. Okay, so let me rephrase again. If you add worst outlier or infinitely large outliers to your dataset, and if the change of your estimator is bounded, even though outliers be extremely large, then your estimator is called bias robust. So this is the intuitive explanation of bias robustness in frequentist context. So we wanted to extend this concept to Bayesian setting. So in Bayesian setting, instead of this point estimator, we have some distribution. So let's say this blue line is the Bayesian estimator, let's say mean of the dataset. But the same things happen again. If we add some outliers here, this red histogram, then your posterior or your Bayesian estimator would be shifted towards the outlier, or shifted in the direction of outliers. Okay, then we can say the same things again. If we add the infinitely large outlier or worst outlier to our dataset, then if our posterior, if this change in our posterior caused by this outlier is bounded, we call our posterior globally biased robust. Okay, so this is the intuitive explanation about the bias robustness in Bayesian setting. So if you want to know the exact criteria or exact formulation, you can also please refer to our paper. So yeah, and if we formulate this concept in some rigorous formulation or in rigorous setting, we can derive in which condition our posterior can be globally bias robust. Okay, so then in the paper we identified some conditions to make our posterior bias robust. Okay, and for example, this robustness criteria or robustness condition can be used to choose nice kernel to define our posterior. Okay. Okay. So it was a quite little bit of rush, but this completes the theoretical parts. Now I'd like to move on to the experiment part. Okay, so the explicit form of our KST-based posterior was as follows: the prior times the exponential of these summations, which is KST, kernel sign discrepancy, and we choose our kernel as follows. Okay, so in interest of time, again, I would have to omit the detailed explanation of this kernel. But this kernel is derived from some derived to make sure our kernel Stein discrepancy have some nice properties. So if you're interested in, yeah, please refer to our paper, or you could ask questions if you're interested in. Okay. So now we check the performance of KST-based posteriors using simple normal location models. So our model is just the Gaussian with mean parameter theta, and we generate our data set using the mixture of Gaussian. So the with mixture proportion epsilon. So the first component of our data distribution is just Gaussian with mean 1 and the variance 1. And the second component of this distribution is Gaussian, but whose mean is, for example, 10 or 20. So this second component represents some outlier noise. And this first component represents the main part of the data set. Okay. And we mix this outlier noise here with, let's say, with proportion 10% or 20%. Okay. And okay, so let me explain about the first row of this figure first. So in this first row, the left figure shows the exact Bayesian posteriors. And the second figure shows KST-based posteriors. And the third figure also shows the KST-based posteriors. But the distinction between second, middle, and the right figures is that this middle KST-based posterior does not satisfy the robustness conditions, which I explained just before. And this right KST-based posterior satisfies the robustness conditions. Okay, so in that respect, I call this right KST-based posteriors robust KST-based posterior. Okay, and this black line, the solid black line, shows the case where we don't have any outlier noise in our data set. And this dot line here represents the case where we have 10% noise in our data set. And this last dot line shows the case where we have 20% outlier noise in our data set. And as you can see, this standard-based posteriors is shifted in the direction of outliers if we increase the proportion of outliers. And on the other hand, this robust KST base stays around the true variable parameters. In this case, 1 is a true variable parameters, and this robust KST base posteriors stays around the true value of the parameter, even if we increase the proportion of the noise in the data set. And this KST base, which doesn't satisfy robustness conditions, sort of interpolates between the standard base and robust KST base. Okay. Yeah. And a second example is exponential random graph model. So yeah, we tried a little bit more challenging application for KST. And this model is also intractable. The previous model of this normal location model was not intractable model because the normalizing constant of this model is analytical. But in this case, we have intractable model whose normalizing constant is very difficult to compute. Okay, so yeah, the takeaway message in this slide is yeah, our KST-based posterior somehow work even with the intractable models. And the last one is discrete model. So our method can be extended to discrete case, not only continuous case. while keeping some strong robustness properties. Okay, so this is the summary of our research. So we propose the combination of generalized Bayesian inference and Stein discrepancy, proposing this form of pseudo-posteriors. And we shows that this pseudo-posterior is computationally efficient and robust, even for intractable models. And this satisfies many nice theoretical properties. Yes, and this work is now published in the JRSSB, so you can find the paper there if you are interested in. Okay, so thank you so much for listening. This is the end of my talk.
Okay, let's speaker again.